number 12 here, we have a equation 2x minus x squared, and we have the equation just y equals negative 3. Alright, so we're going to find the area between these two. I would suggest drawing a graph. These two are, fairly simple to draw because one is a horizontal line here at negative 3, so you know that. This one's just an upside down parabola. So if we draw our graph, let's do a standard window, see what we see here. Right, so we can see that it goes through 0, 0, and bottom line has that general shape. So, question then is, in this region, if we were to draw a rectangle anywhere, the top would always be the parabola and the bottom would always be the line, wouldn't it? So then wouldn't the integral then just be 2x minus x squared minus negative 3 dx for the integrand part? Okay. The issue is, what about these two here? We just need to find those intersection points. We need to know the x values of those two coordinates, don't we? So with that, we could go x squared minus 2x, actually negative x squared plus 2x, that is, equals negative 3. And I'd probably put it on the right side of that. I'd get x squared minus 2x minus 3. If we factor that in minus 3 and plus 1, it'll be negative 1 and positive 3. Alright, and in this particular section, it doesn't say do it analytically, so once we have the integral set up, then what? Alright, put it in calculator. So if we do our 2x minus x squared plus 3. And I would always do math frac, see if it's a fraction, so we get an exact answer if possible. 32 thirds. That would do it. Questions on that one? What else? On 15 we have a general function here. It's of the form x a squared minus x squared, a greater than 0, and then y equals 0. So in general, y equals 0 we know is the x-axis. Let's see if we can figure out what this would equal. If we draw a picture of it, we have x on radical, and let's just pick some a that's greater than 0 just to see what a curve might look like. We can do a diagram if we want to, but ultimately if I let a be 1, I'd have 1 minus x squared in the radical. And if we graph that, zoom in on that a little bit here, see it a little better. So ultimately it looks like that. Okay. And if we were to just to for argument's sake, let's say we made it made a equal 2 and we made that a 4 in there, then what would the graph look like? Okay. All right, so that, and then if we did our put a 9 in there, made a 3, see what that would look like. Notice that each time that we do it, it's getting out further. If we were to zoom back out on this one, notice that it went from negative 1 to 1 on the first one, then negative 2 to negative 2, and then negative 3 to negative 3, and so on. So ultimately, in general, this is going to go from negative a to a, then, isn't it, for a generalized function? Okay. All right, and ultimately the question is find the area of the regions enclosed by the lines and curves. Okay, so ultimately, if we were to set our integral up as such, if we just did the straight up integral on that, okay, wouldn't the answer be 0? Okay. But ultimately they want to know what is the actual area that's enclosed by the curves and lines, etc. So we ultimately want to know that one and treat the negative one as positive, if you will. So you notice with the symmetry here, though, this being an odd function, we could just find, can we just go 0 to a, and then just double it? We just found the 0 to a part right there, and then we doubled it. So if we do our x, a squared minus x squared dx. Now, the reason this is going to be more difficult is because we don't have numbers here, so it's not a calculator problem. We can't just put it in the calculator. Right? So we'll have to use the fundamental theorem here. And is this a known derivative? No. So ultimately from that, then I would probably let u equal a squared minus x squared. And that way du would equal negative 2x dx, which is related to our x dx that we have outside the radical. In fact, negative 1/2 du would be x dx. And so if we set up our substitute integral, we would have radical u, negative 1/2 du. Again, this part is our u. X dx is equal to negative 1/2 du, so we can replace the dx and the x with a negative 1/2 and a du. And again, the u to the 1/2 is our integrand, so if I anti-differentiate u to the 1/2, that'd be u to the 3/2 over 3/2. So it'd be 2/3 u to 3/2. Still have negative 1/2 out in front. And ultimately we'd have 2a squared minus x squared over 3 on 0 to a. And let's do the 3/2. We got the 3/2 power there. Right? So evaluating, if we plug an a in here, what's going to happen if we put an a in? We're going to have a squared minus a squared, which is what? 0. Okay. So ultimately, evaluation part, we'd have 0 for the first part, minus. And the second part, if we put a 0 in there, we're going to get 0 in here. And then we're going to get a squared left inside the parentheses. A squared to the 3/2 is going to be a cubed. So ultimately, we'd have 2a cubed over 3. And we're taking a squared and we're raising it to the 3/2. Power to a power would multiply. 2 times 3/2 would be 3. So we'd have a cubed there. And ultimately we'd have negative 1/2 times negative 2a cubed over 3. 2's would cancel out. We'd wind up with positive just a cubed over 3. Alright, now keep in mind that that's just the integral part. And that would just be the one part, the positive part if you will. So what are we going to need to do to get the total area? On the negative side it'd be the same, wouldn't it? So we just want to double that. So if we multiply that by 2, and our final answer would be 2a cubed over 3. Now, just for argument's sake, keep in mind that that's our answer, 2a cubed over 3. Let's see if that makes sense with the example that we have right here. So if we were to do our integral of x square root 9 minus x squared we would get the following, approximately 9. And so that means if we doubled that, it'd be 18. And our answer, remember, is 2a cubed over 3. If I did 2 times 3 cubed divided by 3, I'd get 18 with that. So even though we can't actually plug anything in the calculator in the general form here, okay, we can see that our answer is actually right if we try different a value. Do it with a substituted into this integral, and put our a, same a in this, the final answer. Because remember, the answer to this right here is this, isn't it? Answering this question, we got 2a cubed over 3. So the area under this curve from 0 to a times 2 to make it double for the negative part, okay, is this. So whatever a we put in here and get an answer, and whatever a we put in here and get an answer should be the same, shouldn't it? And with 3, it worked. Okay. Now, does that make it 100% sure that we're right? I'd feel pretty confident if I were you. You tried 3 and it worked. You can try 4 if you want to, or 5, or something else. Try some other numbers and make sure it works for all of them. Okay, but it should. Okay.
Now, how come when you had the integrated, you multiplied it by 2, you put it 2?
Remember, this integral from 0 to a is just the right branch, the positive part.
Mm-hmm.
We need to double it, though, because we want the area of the left part, too, which is underneath.
Okay, but then why did after, when you got the a cubed over 3, why did you multiply that by 2 again?
remember this was I never multiplied it by 2 in the first place over here. This was still out there.
Still on.
So this a cubed over 3 was the answer to this part right here.
Okay.
So and then we still needed to double it at the end.
I see.
Good one. What else?
You do one like number 9.
Like number 9 or
Or,
you
yeah, just number 9.
Okay.
It's like more like it.
Okay, number 9, we got, it looks like that we have two functions here that when they crisscross at the origin, one becomes the top and bottom, they switch, looks like. So couldn't I just set up an integral then from, looks like negative 2, 0. And then the top function would be the cubic in that area. True?
Yep.
Cubic function be on top. So it'll just be 2x cubed minus x squared minus 5x minus the bottom function in that area would be the quadratic, negative x squared plus 3x. And then on the other part, it goes from 0 to 2, the other intersection point on the right. But this time, the quadratic is on top, and the cubic is on the bottom. And ultimately, what are we going to do to those two? Just add them together. So at the origin, they switched. The cubic was on top in the first part, so that's why it's first, and subtracting the quadratic. And then they switch after that. The quadratic is on top, and the cubic is below. Right. So from there, it's just power functions. So just anti-differentiate, and plug in your negative 2 and 0, and get an answer for that, and an answer for that, and add them together. What else?
21.
21, we got x plus y squared equals 0, and x plus 2y squared equals 3. Alright, ultimately what we might suspect here is that we have some non-functions possibly because it's y squared instead of x squared, which ultimately we know that sideways parabolas are of that form. We have x equals y squared.
No, 3 and 2 are switched. X plus 3 y squared.
Oh, I got it. You're right. Look at the one above it. So ultimately, we recognize that these are sideways parabolas because they're of the form x equals y squared. Okay. And so if we want to graph these, I'm going to show you a way to graph these, which might be convenient for you. If we solve for x and we get x equals negative y squared, and x equals negative 3y squared plus 2, we solve both of those for x. We can certainly graph these by plotting points. We can just plug in y's and get x's and just plot the points that were given. Another convenient way to graph non-functions is to use parametric mode. We'll spend more time on that in Calc BC, but just for our graphing purposes, if we put our calculator in parametric mode, the way we can graph non-functions in a pretty nice manner is to take whatever the equation is in y, put that in our x. So we're going to write negative, and they use t's instead of y's here, but we'll just use negative t squared. And then we'll just use a t always for the y. And then if we do negative 3t squared plus 2, and then again t, the y is always going to be 2. And again, we're going to use this for graphing non-functions like this, when we have functions that are written for x in terms of y. Okay. And so we type it in as such, and we do the window correctly here. In the window, it's gonna plot as many points as you give it here. The t's are going to be the points that we're going to use to plot. I'd probably go like just say negative 3 to 3 and see what we see. T step is going to be, it's going to plot values every 0.13 the way I have it set up. You can just make that 0.1 if you want to, if it's not already on that. And then the same, the x and y window is as normal. So if we go negative 10 to 10, that's fine. So like I said, try negative 3 to 3. We'll see what happens there by putting in those numbers for t. And if we graph it, and we get the following. And we can see that we get what we want here because all we're looking for is where these intersect each other essentially. So I'm going to zoom in so we can see that intersection a little bit better. And ultimately the area that we're looking for is this stuff right here because this is where the overlap becomes. You can see they have two intersection points with each other here. The overlapped part, the area between the two curves would be this. And you'll notice that there's clearly a function that's on the right and one that's on the left in that region. So this would be a good candidate to integrate with y's instead of x's. So the question is, which one of these is to the right and which one is to the left? Well, we know that x minus y squared, that's going to contain the origin, so that's going to be this one. True? And so when we set up our integral, we're going to do right function, non-function I should say, right relation minus left relation. So that ultimately will be our integrand. Because again, the negative 3y squared plus 2 is the one that's on the right. Right? And again, if we do a horizontal slice, that's always on the right, that function. Always on the left is the negative y squared relation. And then the only other issue is what are these intersection points here? Okay. Well, again, the intersection points are when negative y squared equals negative 3y squared plus 2. So if I add that, I get 2y squared plus 2, or equals 2 that is. If I add that, if I divide, I get y squared equals 1. So y would be plus and minus 1. And so these points right here would have y values of 1 and negative 1 where they intersect. So that means negative 1 to 1 would be my points in question. And one of the problems with the parametric mode though is you don't have, if you do the calculate menu, you don't have an intersection command. Okay. Keep in mind that they're going to, a problem like this, they're going to give us a problem that's going to be fairly easy to find the intersection points I should say, which they were in this case. And then at this point, it's a calculator problem. So just put that in your calculator and you'll get the right answer as long as you type it in there, right? So negative 3y squared. Go back to your, go up to change the mode again. Back to function. Type that in there as such. 2 2/3. Or 8/3. Questions on that one? Right.
Like, what mess you up if you just do it in the normal, like, terms of x, like, in the function mode?
I mean, ultimately, if you solve these for y, though, you're going to have two different parts that you're going to have to deal with. I mean, you can solve this for y, you're going to have plus and minus square root of x. So you're going to have to basically graph 4 things.
Or, like, what if you, like, just put, like, y equals negative x squared, and y equals negative 3x squared plus 2? Like,
I mean, ultimately, those graphs are not going to be, it's not going to be the same graph, though. 'Cause you're going to get functions that are up and down instead of left and right, which is not what these are.
like you can't just guess and have, like,
Yeah. I guess you could try and get lucky maybe, but I don't think I would if I were
I
you.
don't think that's the idea.
Oh.
Stupid week, feel that?
Alright, what else?
35.
35 we have, it says the region bounded below by the parabola y equals x squared and above by the line x or y equals 4 is partitioned into two subsections of equal area by cutting across with a horizontal line y equals c. So we ultimately have the parabola, the line y equals 4, and we're cutting this somewhere so that there's two equal sections. And keep in mind that C may be something like that, right, where that area and that area are going to be equal to each other. So that C is somewhere in the middle of 0 and 4 going up, where we have two equal sections. All right. So ultimately here in part A, it says scratch a graph of the region and draw the line C across so that it looks about right. So I did that already. So keep in mind it probably is going to be above the halfway point because there's, this is wider out here than these are wide in the bottom area, if you will. And then it says in terms of C, what are the coordinates of the points where the line and the parabola intersect, and add them to your figure. Well, ultimately, if we want to know when y equals x squared equals y equals c, then wouldn't c have to equal x squared? So it'll be plus and minus radical c would be our values of x. So that means that that point would be radical c, c. And this point would be negative radical c, c. Keep that in mind, we'll add those to our drawing. Alright. And then the part B here says to find c by integrating with respect to y. It says this puts c in the limits of integration here. Okay. So, and then we also have to do it in part c by finding c by integrating with respect to x. Okay. All right. So, bottom line here is if we're going to find where these areas are equal to each other and find this c in question, okay, then we want to find in this problem. Let's think about if we're going to do this with respect to y, that means that our integral is going to have y in it, which means that our slice is going to be horizontal. Okay. And if I wanted to, at this point, knowing that this is y equals 4, and this is y equals x squared, which is also x equals radical y, if you will. If I solve that for x, I would take the square root of both sides. And think about if I did a right minus left situation, and I just did radical y from 0 to 4 dy, wouldn't that give me the area of this right side of the parabola, if you will? So my right function is radical y, my left function is 0. True. So if I found that area right there, let's find it. So if we go, and I do square root x, 0 to 4. Oops, forgot my x. Ultimately, it's, again, using an algorithm. It's going to be 5 1/3, which would be 16 thirds. If we did it by hand. Nope, not 13, 16 thirds. Alright, so that area right there is 16 thirds. And keep in mind, if I were to do the same integral here, and I do 0 to c of our y squared dy equals 8 thirds, wouldn't that ultimately allow me to find c? We know that area right there is half of what this area is right here. Because we want that c to be either right in the middle, or not in the middle of the 0 and 4, but in the middle to create two equal areas. So again, if we know the whole area that we shaded here is 16 thirds, then that half area right there would be 8 thirds. Okay. And so now at this point we have an equation that has c in it that we can hopefully solve for that c. Because if we go from 0 to c, and radical y minus 0, we'll get our half area, which is 8 thirds. So let's do the anti-differentiation here. Be 2 y to 3 halves over 3. 0 to c. C in there, of course, would be 2 c to 3 halves over 3. 0 in there would be 0, and that ultimately equal 8 thirds. And so if we do the cross product here, we're going to get 24. Move it up here. Equals 6 c to 3 halves. Divide that, we get 4 equals c to 3 halves. Close both sides with 2 thirds power. And we're going to get c equals. And if we do 4 to the 2 thirds, 4 to the 2 thirds, there is no cube root of 4. That's a whole number that we can square, but ultimately we can just leave it as such, 4 to the 2 thirds. Okay. And as a decimal, we want to check it, make sure it seems reasonable. 2.5. And what do we say about the c value? Should be bigger or smaller than 2? Should be a little bigger than 2, right? Which seems to make sense then for us. True. Questions so far?
How did you get 24 equals 60 for 3 halves?
Cross product, 3 times 8, 2c times 3. So anytime we have a fraction like that, we can just do the cross product and get c by itself. Alright, now thinking of it from an x standpoint, couldn't we also write the, if we wanted to find c, if you will, here, if we wrote an integral from 0 to radical c of c minus x squared dx, wouldn't that also have to equal 8 thirds? Remember what I've done here is I've this bottom region right here, if I went from 0 to radical c, and I do c, which is this x value, that's or the y value that's on top, and the top function in this region would be the c, The bottom function would be the x squared function. So if I wanted to write an equation with x values instead, okay, then that integral right there would have to equal 8/3 as well, wouldn't it? Still the same region, we're just writing it in terms of x instead of in terms of y. And again, the area of this region is going to be, or a slice here, the top of it is always going to be c, bottom is always going to be x squared, so if I go c minus x squared, that'll be my integrand. Going from 0 to radical c over here. And then I could just do the same thing I did here. I could evaluate this integral, and hopefully, when I get done, I'll end up with what? Hopefully I'll end up with c equals 4 and 4 to the 2/3, huh? So now that we have it set up, we'll try it. I'll switch papers here so we got some space. So I know cx minus x cubed over 3 is going to be our integrand here. Going from 0 to radical c. And if we put c radical c minus by a cube, that's going to be c radical c over 3. 0 and here are going to make both zeros. If I make this 3 and 3, I'm going to wind up with 2c radical c over 3. And remember that equals 8/3, right? And if I do the cross product again, I'm going to get 24 again. And I'm going to get 6 c radical c. It's going to give me 4 equals c radical c. Now, let's change c radical c, because what is c radical c? C to the 1 times c to the 1/2 would be c to the 3/2. And conveniently, isn't that the same equation I had a minute ago? Just going to compose both sides with the 2/3 function. 4 to the 2/3 would give me my c. And either way, got the same answer. So ultimately, again, if I do it in x, you get cx minus x cubed over 3. If I plug in my radical c and my 0, I wind up with this, which, remember, c radical c is just c to the 3/2. Okay. Solve it the same way we did the other one, and we get 4 to the 2/3 is our c value.
What is that 4 equals c to the 3/2?
Yep. Or c to the 1/2 times c to the 1, c to the 1 1/2, or c to the 3/2.
And then what's that, like, rule, like, why do you switch it to the 1?
What's
What
the,
other way to say?
Or, like,
you gotta get the 6 out of there.
or no, the 2/3, like, c.
Right, to get rid of the 3/2 power to get c by itself, we need to raise 3/2 to the 2/3 to make it c to the 1.
Okay.
So. Alright, so bottom line, in a region like this, if we're looking for an area, or we can do it, really, we can do in x direction, we can do the top minus the bottom function. Okay. Or we could do the right function minus the left function, because the function on the right is always this. Okay. Function on the left is always this. So either way, we can set up an integral with x or y in a region like that that has a same top, same bottom throughout, same right, same left throughout. We can do it in either variable. We can do it in x or we can do it in y. And either way, we should wind up with the same answer. Questions on that one? All right, let's we're gonna